Are y'all ready to start the notes? Okay, so this is a lot of definitions and labeling. In the past, I would have printed out a wave and we would have labeled it together, but that's not how we have things. So my advice to you is to go on Google and look up these waves and save the image to your drive. Because those images on Google, they're usually labeled. They have the amplitude, the frequency, the wavelength labeled. So if you ever need to go back, you have those pictures on your drive already. Or you can just draw it in your notebook, however you want to. It's up to you, but that's my advice. It's just to save a picture. So today we're talking about mechanical wave properties. We talked about the two waves yesterday. We said transverse goes up and down. And then longitudinal just goes side to side. And that's what we're going to be talking about. And we're going to be talking about how to read those waves. All right. And then you do have an assignment over mechanical waves. So the good thing is we're not doing any math today. It's just all concepts, all definitions, all labeling. So a wave, again, is a disturbance that travels or propagates from the place where it was created. So we can say it's a wiggle in time because, well, waves wiggle. A mechanical wave is a wave that does require a medium. So it needs a solid, it needs a liquid, or it needs a gas. Remember yesterday we said in space, no one can hear you scream because there's no sound in space. So if you're knocking on your desk, that's sound traveling through a solid. If you're swimming in the water and you're screaming underwater, that's sound traveling through a liquid. And then sound traveling through a gas, well, that's us talking right now in the air. Waves are traveling. So we did mention transverse wave. Again, it's perpendicular. We say it's perpendicular because it's going up and down and side to side. So these placements are going to be at right angles of each other in the direction of motion. And we just say it's a right angle because these waves aren't slanted. They're not crazy angles. They're just up and down, side to side. Don't worry, you're never going to have to measure the angle of a wave, so don't think about that. So we have some parts to a transverse wave. We have crest, trough, equilibrium lines, amplitude, wavelength, period, and frequency. And those are the words I said that we're going to be labeling. So if you want to find an image on Google that has all of these labeled on a wave, save that image. If you want to write it in your notebook and draw it, draw it. But I suggest you find an image and you save that image. So crests are going to be the highest point in a wave, and we're going to call this a positive displacement. So crests are at the top. They're always going to be at the top. That's how crests work. Troughs are going to be at the bottom part. These are going to be the lowest part of the wave, and we're going to call this a negative displacement. So crests are at the top, troughs are at the bottom. The equilibrium line is exactly what you think it is. It's the line in the middle of the wave. So this is a imaginary line. Waves don't actually have this line. We draw it so that way we can measure amplitude. It's not a real line. Again, it's imaginary. We draw it so it can help us. It's a middle line between crest and troughs. It's dividing the wave horizontally. And the wave oscillates around this line. So it moves back and forth around this line. But again, it's an imaginary line. It doesn't really exist. So amplitude is basically the height of the wave, except it's not measured from crest to trough. It's measured from the equilibrium line to the crest or from the equilibrium line to the trough. So this is amplitude. Again, it's the height. It's the maximum displacement of a wave. We do measure amplitude in meters. And depending on the waves, sometimes it can be a very high amplitude, sometimes it can be a very low amplitude. It can be in millimeters, it can also be in kilometers, depending on what type of waves we're using and what type of waves we're talking about. For example, AM and FM radio waves can go a longer distance, so they tend to have a higher amplitude. Wavelength measures the length of a wave. It's the distance between two identical parts. So keep that in mind. I don't think we have to measure wavelengths this year because we don't have rulers. I mean, we have rulers, but you can't use them. So I don't think we have to worry about measuring wavelengths, but just keep in mind, it's always two identical parts of a wave. So if you're doing crest to crest, you're doing troph to troph, they just have to be the same part. The symbol for wavelength is an upside down Y. That's what I like to call it, upside down Y. And it's still measured in meters because, again, it's still a length. This can also vary too. We're going to have short X-rays, and X-rays are very dangerous because they have such a tiny, tiny wavelength. Because they have a tiny wavelength, they're going to have a higher frequency, and that's what's dangerous. That's what can kill you. Radio waves, however, are very safe, and that's because they have a long wavelength. So they have a very low frequency, and that frequency is so low, it's not affecting you at all. If you go outside right now, we have radio waves and AM, FM radio waves going on like crazy. Do you feel any of those waves when you walk outside? No, because their wavelength is so long, their frequency is so small, you don't feel those waves. Now let's go to an X-ray machine. Y'all have all been around an X-ray machine, right? Where they take X-rays of your teeth when you're at the dentist's office. Okay, you can hear that drum vibrating. You can hear those waves going on. Maybe it's all in my head, but I swear I can feel vibrations when I'm stuck under that little thing. I don't know. It's probably all in my head. Point of the story is X-rays are bad, radio waves perfectly safe. So cycles, transverse waves run in cycles. A cycle is one complete wave. In this example, how many cycles do we have? Well, this is one wave. This is a complete wave because it's two identical parts. This is another, two identical parts, and another, two identical parts. So that's 3 cycles in this wave. Again, it has to be identical parts. You can't have it starting at the equilibrium line going to a troph. Those aren't identical. Those 2 points won't count. A period is the time it takes to complete one wave cycle. Symbols big T, unit is seconds. This is one of the questions you had yesterday that I told you to skip because we didn't talk about it yesterday, but we're talking about it today. Oops. So we do have a formula for period, but we're not gonna learn it until tomorrow. I just wanted y'all to see what it looks like. It's the time over number of cycles, but tomorrow we're gonna do all the math. No math today. Frequency is the number of waves passing by a specific point per second. So time is the time it takes to complete a wave. Frequency is how many waves we have in a full second. Frequency has the symbol of an italicized F, and it's measured in hertz. Again, here's the formula for frequency. It's just flipped from time, period, sorry. We're just flipping these around, but we won't do any math today. We'll do all the math tomorrow. So the average heart rate is about 1.67 hertz. That's 100 beats per minute. Radio stations like Mix 96.1, they have a frequency of 96.1 megahertz or 96,100,000 hertz. That's how the frequencies work. A microwave oven uses a frequency of 2,450 megahertz or 2,450,000,000 hertz. The bigger the frequency, the safer it is. Don't worry about it. No, that's a lie. The bigger the frequency, the more dangerous it is. But these are good frequencies. We like these frequencies. These are safe to be around. Safe to be around a microwave. It's safe to be around radio stations. Again, these are just the formulas. They're inversely related. They're flipped from each other. All right, now we're talking about longitudinal waves. These are waves, again, that go parallel to the direction, meaning they go side to side, only side to side. They don't go up and down. Sound is a perfect example of longitudinal wave because it is going sound to sound. It's pushing on those gas molecules. So we do have properties of sound too, just like we have for the transverse wave, we have them for the longitudinal wave. Some sound waves are going to be pulse waves, meaning they're short-lived. Some sound waves are going to be periodic, meaning they're going to last a long time. We have compressions and rarefractions. I always mess up on that word. So compressions are going to be the tight springs where they're tight together. Rarefractions are going to be where they're spaced out. Crests would be considered compressions. Troughs would be considered rarefractions. But since it's a longitudinal wave and not transverse, we don't call them the same thing. Compressions are going to have the high pressure, meaning their molecules are going to be closer together. Rarefractions are going to have low pressure, meaning the molecules are more spread apart. Hello. We can still have amplitude for sounds. It's still going to be the same as a transverse wave. It's going to be from the amplitude equilibrium line all the way to the top, or equilibrium line all the way to the bottom. And the amplitude of a sound wave is going to decrease with distance. The farther the sound travels, the less energy it has. And that kind of makes sense. If I'm talking from one corner of the room, obviously you're going to be able to hear me if you're standing in that corner with me. Versus if I'm talking in one corner of the room and you're way over there on the opposite corner, you're not going to be able to hear me as well, because by the time my sound gets to you, it doesn't have the same energy as it does when I first started talking. Some of the energy is going to be absorbed by the objects around you. So like in a classroom, the desk would be absorbing my energy of sound. The floor would be absorbing it, the chairs, even the gas in the room would be absorbing the energy of sound. That's why when you're making, no, never mind, we won't talk about that. Wavelength is also going to be the length of a wave. It's still going to be two identical points. So you can do compression to compression, or you can do from refraction to refraction, but it has to be identical points. It's still going to have the same symbol, and it's still going to be measured in meters. And then we have frequency of the sound, which is the same as a transverse wave. It's the number of waves that pass through a point per unit of time. These are the formulas, but sorry, we're not going to be using the formulas until tomorrow. All right, so this is a hearing test. I don't think y'all can listen to it at home. So if you want at home, read the PowerPoint video, play this video. You could hear it on your own so you could test your ears. Everyone in class, I'm going to play this video once I'm done with the PowerPoint. And basically, it's just high frequency pitches to see what you can hear, to see what you can hear. Period, it means the same thing for a transverse wave as a longitudinal wave. It's the time it takes sound to complete one wave cycle. Again, we'll do these formulas tomorrow. Speed of sound is going to vary greatly depending upon the medium it's traveling through. And we're going to talk more about this tomorrow, but I just want to talk about it briefly today. So sound is going to travel faster in different types of mediums. We have ice, water, and air. Sound's actually going to travel faster in solids than it does in a gas. Meaning, if you have a long metal pole and you're hitting it, that sound's vibrating through the metal pole a lot faster than you are talking around the metal pole. Again, sound travels faster in a solid than it does in a gas. And that's because it has more molecules to bounce off of, because in a solid, molecules are tighter. In gas, they're more spread out. Temperature is going to also affect the speed of sound. Sound's going to travel faster when temperatures rise. So I don't think anyone's ever done this before. It's kind of a lost thing. But if you ever go fishing at night, or if you're ever outside playing baseball at night, or if you're ever just outside sitting around at night, you might notice that you can hear things a lot more clearly than you would during the day. And that's just how sound travels. Sound travels much slower than light. Of course, nothing beats the speed of light, right? Light always travels the fastest. That's why you can see fireworks before you can hear them. That's why you can see lightning before you can hear the thunder. Because again, light's traveling faster than the sound is traveling. You can see the light coming to you a lot faster. By the time the sound comes to you, the light's already gone. All right, that's all I needed to talk about today. Go ahead and do your assignment over mechanical waves. And then everyone in class, I'm going to play that video for you.